In sections 2 and 3 of chapter 5, we learned about indefinite integrals, and now we're going to turn our attention to the definite integral. And to understand the definite integral and be able to apply it, to me, you have to understand the idea of summation notation. Many of you might be familiar with the idea of summation notation, but we'll have a little bit of review and develop some formulas. Okay, so let's take a look at this example. This is an example of summation notation, and there's a few things that we want you to keep in mind. That the summation sign is this letter. This is the capital sigma, all right, in the Greek alphabet. All right, in this summation, the lower limit of the sum is 2. Notice that appears at the bottom underneath the summations sign. Sometimes it appears underneath and to the right. The upper limit is 4, and the index of the limits, we could kind of think of this as a variable, is j. All right, now what this means is, think of the lower limit as the starting point and the upper limit as the ending point. And think of it this way, that j takes on the values starting at 2, and then it increments by 1. So it goes from 2, then to 2 plus 1, 3, then to 3 plus 1, 4. And since 4 is the upper limit, all right, that's where we end. Right? Now, if j is equal to 2, if I look at this expression here, all right, 4j minus 5, that would become 4 times 2 minus 5. And if j is 3, I'd have 4 times 3 minus 5. And if j is equal to 4, I'll have 4 times 4 minus 5. And this, now if I add these expressions together, the j equals 2 expression, the j equals 3 expression, and the j equals 4 expression together, what I'll get, well, of course, 8 minus 5 is 3, plus 12 minus 5 is 7, plus 16 minus 5 is 11. I'll get 21. So 21 is the value of this summation. 21 is the value of this summation. Let's take a look at another example. Okay, so again we have a sum. And notice I point that out because there's another symbol that's pi, the capital letter pi, that means multiply. But of course we don't have that here. We have a sum. And let's see, the lower limit of the sum is 3. That's the starting point. The upper limit is 6. That's the ending point. The index in this case is k. As we can tell because we see k equals 3 to 6 here. So we'd let k take on the values starting at 3. And then index by 1. 3 plus 1 is 4. I should say increment by 1, I'm sorry. And then 4 plus 1 is 5. And then 5 plus 1 is 6. And then we're at the upper limit, so we stop. When k is 3, I won't write out as many details. I would get 9 minus 9 is 0. When k is 4, I would get 16 minus 12. 16 minus 12 is 4. When k is 5, I'd get 25 minus 15, which is 10. When k is 6, I would get 36 minus 18, which is 18. And so I'd add these together because, after all, this is a summation. And so this would become then, the value of this summation will be 0 plus 4 is 4, plus 10 is 14, plus 18 is 32. So these are examples of summations. Now, there are certain properties that summations have, and that is, first of all, if you have the summation of a constant. Now, remember that the variable, think of the variable here as k. as the index k, and c does not depend at all on k. So c is a constant multiplier, a constant factor. Constant factors can be taken out. Let's take a look at why that's true. Because if we look at the sum, I'll take a specific example. Sum as k goes from 1 to 3 of c times a sub k. That would be c times a sub 1 when k is 1, plus c times a sub 2 when k is 2, plus c times a sub 3 when k is 3. And now we're at the upper limit of the sum, so we stop. And notice all terms have a common factor of c, so I can take that out. And if I do, I'll have c times the quantity a sub 1 plus a sub 2 plus a sub 3. And this would be c times the sum as k goes from 1 to 3 of a sub k. So in essence, I can take constant multipliers out, and it's basically just the distributive property that I'm using. All right, if we have a summation of two terms, we can take the sum separately. We'll do the same thing. I won't quite write it quite as long here because this one, well, I guess I can. The sum is k. Let's take a look at why this is true. The sum is k goes from 1 to 3 of a sub k plus b sub k is a sub 1 plus b sub 1 plus a sub 2 plus b sub 2 plus a sub 3 plus b sub 3. All right, and that, because of addition is commutative, all right, well then this would be a sub 1 plus a sub 2 plus a sub 3 plus b sub 1 plus b sub 2 plus b sub 3. And notice this would be the sum as k goes from 1 to 3 of a sub k plus the sum as k goes from 1 to 3 of b sub k. Okay. And then finally we have the difference, and now this is really depends on the first two. All right, I can think of this way. This would be the sum as k goes from 1 to n. Now, by the way, I didn't write these out for arbitrary n. I used 3 as the upper limit of the sum. And n is the statements talk about n in general. And we could do that. It's just that the notation would be a little bit more complicated, so we won't do that right here. But this one we can now. If with these in mind, we can do this last one. So let's take a look at the sum as k goes from 1 to n of a sub k minus b sub k. That would be equal to the sum as k goes from 1 to n of a sub k plus negative 1 times the sum is times b sub k. All right, and this would be, now I have the sum of two things, like in number 2 here. So this would be the sum as k goes from 1 to n of a sub k plus the sum as k goes from 1 to n of negative 1 times b sub k. And now notice this negative 1 is a common factor like the c in part 1, so I can take that out. So this would be the sum as k goes from 1 to n of a sub k plus negative 1 times the sum as k goes from 1 to n of b sub k. And then, of course, when we're adding negative 1 times something, that's just subtracting it. So this would be then the sum as k goes from 1 to n of a sub k minus the sum as k goes from 1 to n of b sub k. And there we have it. The sum of the difference is the difference of the sums. So we have those three properties of sums. I'm going to introduce just one formula, and we're going to build on this next time. This is the sum as k goes from 1 to n of k to the 0. Well, of course, k to the 0 is 1. And so this would be the sum as k goes from 1 to n of 1. And now if we think about what this would be, when k is equal to 1, this is going to be 1. When k is equal to 2, this would be 1. When k is equal to 3, this would be 1, and then we'd keep on going like this all the way out to when k is at the upper limit n, this would be 1. And so notice we'd have 1 plus 1 plus 1 plus 1 n times here, all right, for each of these values of k. And of course, when we add up 1 n times, we get n. So the value of this summation would be n, okay? We can use that well, I guess we can't here. What we'll do is we will develop formulas that will allow us to sum something like this. It would be inconvenient to write out because there's 50 terms, but we'll develop formulas that will help us with this in the next video.